Okay, off we go. I'm fairly sure that Canvas is back and operational. Okay, good. So don't forget, we're maybe a little out of habit then because of the mix-up on Monday. But attendance quiz, attendance code, don't forget to do that. Clock's ticking. You got probably about a minute and a half left. Okay, so last time we were talking about integrals. In particular, change of variables as a technique for how to compute integrals. Very, very powerful technique. Sometimes when you just, the old-fashioned way, just slice and dice your domain, you get these terrible bounds and terrible resulting integrands, and it's sometimes just intractable. So change of variables is a way to change the domain. Right? Really powerful idea, and we saw some cool examples. A neat, cool example, sort of arguably the best example, is integrals in a coordinate system. We talked through these details last time. The polar coordinates conversion formulas can be thought of as a function, and of course I've been pushing that point of view for a while, but thought of as a function. They're a change of variables function. And in fact, they're an excellent change of variables function. And you can compute the Jacobian determinant. There's an easy little convention you can adopt. Stuff that we like anyway. I don't really like negative values of R, right? The positive ones are easy to work with. It's easier to visualize. So small little price to pay, and you don't even have to worry about the absolute values. Right? So this is a really neat system, and likewise for cylindrical and spherical, by the way, and so we talked through these details last time as well. We're going to get to, practical using of these change of variables functions in a bit later today. So we did this first example, and we saw that you can take this undesirable domain here and pull it back to a rectangle, which is totally awesome. Makes the bounds much easier. Look how nicely this calculation went through. And then we made an even better realization. I don't even have to draw the pullback. Theta slices, sort of the very first step in slicing up your pullback domain. I can see them in the XY plane. It is just as good to think about how, visualizing them here and using the original domain versus visualizing them here and using the pullback domain. It's all the same stuff. You're going to get the same answer, so why not do it the easy way? And we saw an example of that, where, again, same example we've already done, but just to see the bounds over here in the XY plane, just interpreting theta slices appropriately. Alrighty, and I think let's see here. Somewhere along in here is where we wrapped it up. So why don't we go ahead and redo this example because I don't remember where we were in it. So we've got some integral. The domain is the unit disk, so that's this region here, like this. Okay. Now again, you can do this the old-fashioned way, and of course you're going to have square roots and undesirable. So, okay, let's do this differently. We're going to do this in polar coordinates. Don't forget to write down not only the polar differentials, but don't forget to put your stretching factor in there. I like to do that as I'm writing my differentials, because once I start thinking about the geometry and the bounds and the slicing, etc., I just might forget. Okay. All right. Okay, so let's start thinking about the bounds and our very first value of theta. If you look at your theta slices are like so. You're going to start with theta equals 0 and then go all the way around until you get to here where, it's going to feel like you're pointing back in the same direction. But do keep in mind, you have gone all the way around. Theta has increased all the way up to here. So by the time you get back around to here, that's actually theta equals 2 pi. If that seems a little weird, don't forget what we are actually doing, right? There actually is a pullback domain. And the slices that you make as you sort of go around, you're like, oh, wait a minute, but I'm pointing the same direction. That's just a visual aid. You're looking at a rectangle in the r theta plane, and 2 pi is just not the same as 0. Does that make sense to everybody? Right. So it seems a little weird until you think about it this way, and then it's perfectly natural. Okay, so our theta bounds then 0 to 2 pi. By the way, good general rule, when your domain, loosely speaking, goes all the way around the origin, always going to be the same bounds for theta, always 0 to 2 pi. So it's a nice little thing to remember. Okay, now we will fix a value of theta. Think about our next, wrong color. Think about our next differential, dr. So what's the range of values for r here? Well, I mean, again, it's just a matter of looking. We're going to start there where r is obviously 0. We end here, which is on this curve, which you could write an equation for. Now, you're going to be tempted to write the usual, there's the unit circle, so x squared plus y squared equals 1. Do keep in mind that's the rectangular equation. We're doing business in polar coordinates. We need the polar equation for that circle. And conveniently, that equation's even easier. The equation for the unit circle, polar coordinates, r equals 1. And on that curve, r equals 1, what is the value of r? Well, it's 1. And again, sometimes you get freebies. How we doing? Everybody happy? Okay, so we've got our r bounds and our theta bounds, and then it's all details from there. Our integrand was this. Of course, we've got to plug that in. Now, again, if you want to explicitly plug in x is our cosine theta and y is our sine theta. In other words, explicitly plugging in the change of variables function. Fine. Feel free, right? But you can also just remember that we've done a lot of that back in chapter 1, and we already know what square root of x squared plus y squared is. It's r. Do keep in mind we have already promised that we will only use non-negative values of r, so I don't even need to think about absolute values. It's just r. Is that cool? Yeah? Okay. Don't forget your stretching factor. And we're in business, and we have a nice, convenient, iterated integral. It's easy to compute with. Make sure you can do those details, of course. And so much easier than dealing with lots and lots of square roots. Everybody happy? Yeah.
How, I know you're not supposed to, how could you have put it negative?
How could the what now?
How could r have been negative?
Oh, well, just, the r theta plane, if we go back to here, the r theta plane is a plane, and r is allowed to be negative. In just regular old doing business in polar coordinates, there's nothing wrong with a negative value of r. You plug in negative values of r here and interpret the way we always have, these equations work just fine, right? So you have to promise not to do that, because we want to be able to say the absolute value of r is r, and that's only true if you promise to stay over here and not to go over there. Does that make sense? Mm-hmm. Yeah. Okay. All right. Let's see here. Okay, so we're going to do a few more examples. Couple of tips. This is not quite an always thing, but it's so close to always, it might as well be for all practical, certainly for Math219 purposes, just always use dr d theta. There are many situations where it doesn't matter and you can do either one equally conveniently, but there are many, many situations where it's strongly preferable to put the dr on the inside, because r tends to be a function of theta, more so than vice versa. Overwhelmingly often, this is at least as good as any other option, so we might as well just do it always. Okay. Another little tip. I suggest that when you write down your differentials, always write down your stretching factor at the same time. This is just a human psychology thing, but again, I commented on this previously. It's pretty easy to start thinking about the geometry and the slicing and therefore the bounds, etc. and just kind of forget. And I see it all the time on student papers. Glad to say that the bigger a deal I make out of it, like I am now, the less often I see this problem, right? And even in my own, stuff, when I'm writing out solutions, I have in the past forgotten to put my stretching factor in there, and oh my gosh, and it's not that I don't know. It's not that I don't understand. It's that I forgot, right? So, everybody has to deal with this. We all have a little bit of forgetfulness. So why not, develop a habit that will combat that forgetfulness? I think this is a really good idea. You don't have to do it. I can't tell if you did or didn't. But I think you'll find it will, reduce, whoopsies. Okay, and then again, this is, as always, think about, when you're looking at particular bounds, there's a relevant point that represents what that bound comes from. That point will be on a curve. That curve will have an equation. In that equation, you solve for your bound. Okay, just like everything else we've ever done. Okay, here's another example. This is a weird example. So our domain is this, what we call an annulus. It's like I don't know why, I think of a moat surrounding a castle. That's just where my head goes. So for whatever reason, maybe I want to compute the amount of, alligators in the moat, and I know the alligator population density, something like that, right? So how would I compute an integral on this region? So one thing you could try is to say, well, I'm going to look first at the integral on the whole disk, and then I'm going to subtract the integral on that inner disk. Right? Green minus purple would leave us the moat, right? Can't do it. Doesn't make any sense. Both of these integrals are nonsense. At least as far as what we've defined so far. Because you gotta keep in mind, the integrand, if you're gonna even define an integral, the way we've done it so far, the integrand has to be continuous. And this one is very much not continuous at the origin. In fact, it's not even defined at the origin. Right? So we have a real problem there. And you may be thinking to yourselves, well, we could, there's probably a multivariable version of improper integrals. Y'all remember improper integrals from Calc 2? Yeah, so isn't there a multivariable version of that? It's actually pretty sticky business, right? So, basically, no. So I'm going to say this is a crash and burn. Nice try, didn't work. Okay. All right, now here's another thing you could do, and I really don't recommend it. You could break up your domain into pieces, like there's that piece, and there's that piece, and there's that piece, and there's that piece. And you could say, I'm just going to do this in rectangular coordinates, and, these are the 4 separate pieces that I'm going to have to do. Now you're doing 4 iterated integrals, all of which have square roots in their inner bounds, because all of them have circles as part of their edges. So very undesirable. We don't want to do that either. And look how easy it is in polar coordinates. There's nothing to it. Our theta slices, if you want to know the range of values of theta, there's what a theta slice looks like, for a given value of theta. We're looking at just that. And, we go all the way around. So 0 to 2 pi. Yeah? Now, for a given value of theta, let's just fix a value of theta and ask, okay, where does R start? Well, R is going to start at that point, which is on this curve, which has that equation given. I need to solve for R in that equation, and that's pretty easy to do. R is 1. So, lower bound, nothing to it. And then likewise, you think about the upper bound, it's basically the same deal. The upper bound is going to come from that point, which is on that curve, which has that equation, which gives that as your upper bound. And we are in business. Not only do we get a polar coordinate integral, but it's an easy integral. You can Do it in your head. Everybody happy? Okay. All right. By the way, I glossed over, but let me emphasize now. Don't forget your stretching factor. Don't forget, I strongly urge you to write it down as you write down your differentials. You'll never need drd theta without also needing the r also. So you might as well write them all down at once. Okay, here's another one. Not quite as convenient, but I think it's still a pretty big win. Weirder shape here. We're looking at the part of this disk that is not in that disk, right? So we get this kind of crescent sort of, let's see, what would, sort of a solar eclipse looking thing, right? Okay. We're going to do it in polar coordinates. Don't forget to write down your R as you write down your differentials. Oh, yeah, question.
For the last example,
yeah.
In the R, would our stretching factor be the difference of the big R minus the little r? Or?
The stretching factor comes from what your change of variables function is. And since we're doing the integral in polar coordinates, the change of variables function is the same old polar coordinates change of variables function. So conveniently, when you're using polar coordinates, it's always R. Yeah. Does that make sense? Okay. Good. Anybody else? Okay, yeah. So what to do here? Let's think about the range of values of theta. Here's the first mistake that students will make. I see this regularly. We know theta represents an angle, right? Very often students kind of interpret a little sloppily, but as measured from where? Very often students, I'm not sure of what the rationale is, but they like to go off of whatever the center of the thing is that they're looking at, and that's just wrong. That's just not how theta is defined. Right? So you gotta remember, very importantly, theta is always measured out of the origin. Right? So our theta slices look like this. Specifically. You got to use the origin. Is that satisfying, right? Okay. All right. Okay, so there's a generic theta slice, and let's think about first and last. Let's look at the last, just because, let's look at the first. Okay, fine. You look at these various theta slices, and the first one comes from that point right there. Now, there's a couple of ways that you can go on this. This is perfectly reasonable. You could say, well, that is on this curve that has that equation, and it is also on this curve which has that equation, and then you could look at both of these equations and then solve for theta, and that works just fine. There's an easier way. This happens sometimes. I encourage you to be on the lookout. Sometimes life is good. Let's just notice, no algebra required, that point, because it is on this unit circle, I know that these two distances are 1. And because it is on this unit circle, I know that that distance is 1. And we've got ourselves a little equilateral triangle there. And so we don't have to do any trig. We instantly just recall that the size of this angle is pi over 3. Is that cool? Everybody happy with that? So keep on the lookout. This kind of thing happens. This is not super rare. And it saves us a little trouble. Okay, now of course, do keep in mind we're looking for a coordinate. Coordinates can be negative, and in fact, this is a negative angle, and so that's why we get negative pi over 3. And then an analogous argument up here. Looking at that point, we get another equilateral triangle for morally equivalent reasons. Positive pi over 3. Cool? Okay. Okay, so now let's fix a value of theta. And, excuse me, think about the, on that theta slice, where does R start, where does R end? Start at that point, which is on that curve, which has that equation, where R is easy to solve for. It's 1. And it ends at that point, which is on that curve, which has this equation. Now, I will pause here and note that this equation was not given, right? This equation, I had to do a little bit of work to get to this. Let's think about, just have a pause. Well, this equation, this curve is the bound of this disk. That disk, we already have this algebra. Right? And the boundary of this disk is going to be where you have an equal sign here. How do we convert a rectangular equation into a polar equation? We consult chapter 1. Right? Basically, it's a matter of plugging in and doing a little algebra. So that is something that you've got to fill in the blanks on. And again, make sure you remember how to do that. This would be a good exercise for you to actually explicitly do. Right? Actually crank out how the equation that comes from this inequality converts to this equation here. Okay, that said, upper bound, this point, that curve, that equation, solve for R, and there's your upper bound. Cool? Okay, don't forget that stretching factor. So easy to forget. By the way, this is another one of these half full, half empty kind of things. And I encourage viewing this in the positive manner, not the negative manner. Knowing that the stretching factor goes here is a big deal. It's going to be worth significant points. Depends on the details of the question overall, how many points the question's worth, blah, blah. Sometimes this could be worth as much as 5 points. That one little thing. Easy money. Take it. Right? Don't forget the easy points. Right? So think of, now again, view this in the negative. Oh, I forgot my R, and so I lost 5 points, and that stinks. Got to think of this in the positive way. All you have to do is do this one little thing, and you get significant points. And I'm not promising 5, but it has been on past exams as much as 5 points. It might only be 3. I don't know. It depends. Okay. How we doing? Everybody on board? Okay. So this next example, I wrestle with myself every year. We arguably don't quite have time for this. I'm going to suggest y'all read this mostly. It is a very clever idea. What you're going to notice is in these first couple of steps, the big ideas of these first couple of steps is not so different from the big ideas of one of the AHPs that y'all are currently in the process of working on, about when you have a function of a single variable in an iterated integral and how you can, what's treated as a constant and how you can move things around. So a lot of the same ideas here. So I encourage you to take a look at this. What's neat about this is that it allows us to evaluate an integral where the single variable fundamental theorem of calculus is kind of crash and burn. We can't find an antiderivative for that function. So you can't just say, oh, improper integral, and I'll just do it. No, you'll run into a brick wall as you try to find the antiderivative. What this trick does is it finds a way to turn that single variable integral into a double integral. And then we just say, hey, we'll do that double integral in polar coordinates, which doesn't seem like it should make a difference. But when you do it in polar coordinates, you've got to put in your stretching factor, and that stretching factor makes your integrand. You've got that extra factor of R in there now, and it makes it an easy U substitution. It's kind of weird how this works. But it's a really powerful idea. And side note, this is actually a pretty important integral. Anyone who's taken a statistics class or a probability class knows that this comes from this thing called a normal distribution, and integrals of distributions are related to how you compute probabilities. And this particular distribution is one of the most important probability distributions out there. So it's a really important integral, and this little tricky idea is how you can compute it. So I think that's cool. All right, make sure to check the details. Okay, so let's move along to cylindrical coordinates. Now, we've already talked a little bit about this. Let's go back and remind ourselves the big idea. Just like with polar, we're going to use the cylindrical coordinates conversion formulas as a change of variables function. We've already computed, y'all presumably, hopefully, have already done this calculation and computed that Jacobian determinant, and yada, yada, yada. Don't forget to restrict yourself to positive r's so you could ignore the absolute values, and it's a lot like polar coordinates. It's very, very similar to polar coordinates. But it's geometrically just that little bit different, and so I think we should do at least a couple of examples. Here we go. Excuse me. So let's see here. Here we go. So the first big observation, here's what a theta slice, keep in mind that means perpendicular to the theta axis. That's what a theta slice looks like in the pullback space. But again, do we really want to have to draw the pullback and do business in the pullback? Everything that happens in the pullback space you can see conveniently already here in XYZ space. And that theta slice looks something like this, right? All theta slices, good old regular old theta slices, they're just kind of half planes. I like to say hinged on the z-axis. Just keep that in mind, and off you go, right? So now again, a couple of tips. I guess I'll zoom back in. You got 6 different options, and it's another one of these almost always things. And I could construct, if I went to some unnatural trouble, I could manufacture an example where this wouldn't be a good choice. But it's pretty unnatural, and I'm not that interested in that. So for all practical purposes, these are your 2 best options, and the big idea is keep your dr d theta together and in the same usual order, dr to the left of d theta. And the only question is, do you put the dz on the outside or on the inside? And again, there's plenty of cases where other options would be just as good, but there are practically no cases where other options would actually be better. So if you restrict your attention to these 2, you won't lose anything. And I think keeping things simple has some value. Okay. And again, don't forget your stretching factor. And again, you can help remember that stretching factor by writing it down all together, all at once, as you write down your differentials. Again, we all have a certain amount of forgetful. And this is a nice tool to combat. Let's just dive in and do one. So we're going to look at our domain as being the upper half ball. So all of that, right? Okay, how are we going to do this in cylindrical coordinates? Well, by the way, I'm going to do this both ways. I'm going to do this same domain. Let's see if I can fit it on. By the way, why am I not full screen? I'm going to do dz dr d theta, and then I'm going to do dr d theta dz. So I'll show you how both options play out. Okay, but let's do them one at a time. So starting with dz dr d theta. D theta on the outside, here's what theta slicing looks like, as we just discussed. half plane hinged on the z-axis. Now, you got to think geometrically, right? So given our half ball, given that this is how we slice it up, I'm going to make a geometric appeal, right? Sort of artistic appeal that this is what the slice actually looks like. Is that cool? Everybody's happy? And another geometric appeal would go all the way around. So 0 to 2 pi. What do you think? Everybody buying it? Cool, cool, cool. So, okay, there's our theta slice. Now we got to ask for the next variable. Let's look at r. R slices represent as I go outward in what you might call the r direction. And those slices are going to, I hope, believably look kind of like that. And let's think about where they start and end. There's the first value of r. That's on the z-axis where r is clearly 0. Is that cool? Everybody happy? Okay. The last one's going to be just that point right there. And another geometric appeal, what's the value of r there? Well, the value of r happens conveniently coincidentally, to also be a radius of that ball. And so there r is a. Does that make sense? Everybody's happy? All right. Okay, so 0 to a. And now, again, and our usual, we're going to pick a value of theta and a value of r. This is our arbitrary representative r slice of our theta slice. And business as usual, right? We go on to the next variable, z. Z starts there, where I think it's pretty clear that it's 0. And then z ends here, and here's where we have to do a little bit of work. That's, thank you, picture, the point that represents our last value of z. It's on the sphere. That's the upper part of the boundary of our half ball. Again, thank you, picture. That sphere has this cylindrical equation. Now, that's another callback, right? Chapter 1. You can write down the rectangular equation, then you convert to cylindrical coordinates. You get this. Make sure you're good with that. And here's where, again, it's really easy to mess this up. Got to remember what we're interested in solving for. I am looking for a z bound, so I need to solve for z in that equation. And solving for z gives me that as my upper bound. What do you think? Is that all right? Okay, let's do it again. Now this time we're going to switch things around. Now we're going to do the dz on the outside. So geometrically, it's going to be a totally different process. We're going to get a totally different collection of bounds. Right? None of this switcheroo simplicity like we would have with a rectangle. Right? So okay, here we go. Z slices. Cutting through sort of like that. Give us sort of discs like this. And again, the first such disc is down here, where again I think it's a kind of a freebie that z is equal to 0. There, right? The last such disc slice up here at the North Pole, where again, luckily, z happens to be a radius. So therefore that value is a. Pretty happy? Okay, now we fix a z slice. Now we move along to thinking about theta. Well, theta slices, and again, geometric appeal. If you think about how a theta slice slices through that z slice, you're going to get little line segments, like so. And I claim they go all the way around, don't they? You know, picture is the answer, right? The picture is the explanation. They go all the way around because that's what you can see in the picture. And so, again, theta goes from 0 to 2 pi. Are we happy? Everybody, feel free to shoot a hand up if you got a question. Okay, and then as usual, now we're going to fix both z and theta. We're going to restrict our attention just to that little twig there. Now we're going to look at r. Well, r starts there where I'm going to say it's obviously 0. And it ends here, which I can see from the picture is on the sphere, which has the same equation we had before. And here's where a lot of students mess up again. And again, easy to mess this up. So easy. So easy to mess this up by saying, oh, well, I already did the algebra and we already found, and so that must be the bound right there. And no, it's not right. Because over here, when we got this value, it was a value of z. That's what I got when I solved for z in that equation. That's not what we're doing down here. Now we're looking for a value of r. So I need to solve for r in that equation. And so I get something a little different, importantly different. Everybody happy? Questions? Feel free. Okay, so it's I hope y'all are starting to get the sort of the feel of the process, right? It's really just like every other kind of integral we've done. It's this kind of slice, find the bounds, fix a slice, go to the next most inside variable, and repeat. Just like every other kind of integral we've done. Again, the geometry is the main thing that changes. So let's talk about spherical coordinates now. And again, again with the pullback and you don't need to draw it, and we just need to reinterpret what the slices look like. And again, we've already computed our stretching factor. So these kinds of slices, what do they look like? And it's going to turn out that overwhelmingly often we're going to want to do theta slices on the outside. Theta slices look like that. Overwhelmingly often afterwards, we're going to want to do phi slices. Now, let's think about for a second, what is a phi slice? A phi slice represents a constant value of phi. What does that look like in an XYZ world? Well, phi is angle off of the z-axis. A constant value of the angle off of the z-axis is going to make a cone. Does everybody see that? So, since we're going to be doing our phi slices of our theta slices, really weird and scary though this looks, I mean, I don't own any knives that would allow me to cut like this, right? That seems very strange, but I don't need to make cuts like this. I'm going to be doing these kinds of cuts of my existing theta slices, and a blue conical slice of that green planar, half planar slice is just a line segment like that, which is nice. Does that make sense to everybody? And then you look at where row begins and where row ends, and the geometry there is pretty familiar. So, okay, so pretty nice as it turns out. Again, pretty much the same tips. Super good news. Again, there is a overwhelmingly as good as anything else option for how to order your differentials. There are precious few examples where this isn't as good as any other option. So, and for Math219 purposes, I don't anticipate us encountering any of the counterexamples. So just always do your differentials in this order. D rho, d phi, d theta. Just default to that. I mean, extremely unlikely you would see anything where this is not just as good as anything else. And plenty of cases where this is way better than anything else. Okay, so that is the order to do them. And again, don't forget, when you write down your differentials, don't forget, write down your stretching factor at the same time. Right? So this whole thing, write it down all at once. Again, as I said with polar, you will never need these spherical coordinate differentials alone without also needing that stretching factor. It doesn't make any sense to wait. Right? Write this down all at once. Rho squared sine theta, rho d phi d theta. I'm going to make sure to memorize that whole thing. It's just super, super useful. Okay. And again, lots of points. And again, glass half full, etc. That's all the same.
Wait, is that always the stretching factor?
Yes, this rho squared sine phi is always the stretching factor, and I'll flash back to, oh, whoops, that wasn't the right button. Yeah, so exactly, rho squared sine phi. Yep. Okay. Oh, and again, while we're here, let's also make sure to remember, always choose, very importantly, always choose exactly the values of phi that you would prefer to use anyway. Right? So again, it's a small price to pay. You just have to give up the freedom to do weird, unnatural stuff that no one would want to ever do. So small price, but you have to do it. Otherwise, the absolute values will come into play and matter, and then you get wrong answers. Right? So it's a weird requirement, but it is an important requirement. Okay, back to where we were. Let's see here. Let's proceed to the example. So here we have a ball, not centered at the origin. The center, how did I miss that? The center is up here on the z-axis, sitting above the origin by an amount that's the same as the radius, and so this kind of sits on top of the xy plane at the origin. Does that make sense? Everybody happy? Okay, rectangular coordinates is a nightmare. Cylindrical coordinates would help. But you will still end up with some square roots, and nothing's going to be perfect. But that is it's definitely an improvement, but still not as good as we would really like. So let's use spherical, and the usual game. Here's what a theta slice looks like. Here's what you get when you make that theta slice through our solid. And again, geometric appeal, that goes all the way around. You just got to see that from the picture, right? And so 0 to 2 pi is cool. Everybody's happy? Okay, now you don't have to do the next step. I find this useful, though. We're going to be thinking about angles, phi, that look like this as we think about our phi slices. And the weird thing about looking at this picture is that here's a right angle, and that does not look like a right angle. Right? You feel like, wait a second, from the z-axis to the y-axis, that's a right angle, and this is a little further. I mean, it feels, just looking at the picture, this looks like more than a right angle. But it's not. It's, in fact, a right angle. So the pictures get a little bit distorted, and this is because we're looking at it kind of in a weird way. It's like, we're looking, instead of straight on, we're looking at a tilted sort of an angle. So my little hack, you don't have to do this, but I think it's helpful is to just redraw that theta slice in such a way that you are looking straight at it. Right, just turn your perspective just that little bit. Right, and now when you're thinking about your angles, right, phi angles look correct, and so it's just a little bit easier to do business. So that's for your consideration. I have no position on whether you actually do this. I think it's helpful. Okay, so here is what a phi slice looks like, and we think about start and end. We start there, which of course is actually there, which is where phi is equal to 0. And then we end, this is a little bit strange, we're going to end, let me get into the pencil mode here, these slices, come on, I can do better than that. These slices, you'll notice they get shorter and shorter and shorter until they kind of finally just barely disappear there, where phi is pi over 2. Now keeping in mind, that's actually that. It's just easier to see that it's a right angle when you've redrawn it like so, instead of that. Is that cool? I mean, questions, feel free. Cool. So we got our theta bounds, we've got our phi bounds, and now we got to think about our rho bounds. You start at the origin. The origin's where rho equals 0. Again, you freebies, that's nice. The upper bound, okay, it's coming from that point. That point is on this circle. Wait a minute, that circle, let's not forget where that circle came from. That circle is actually this cross-section of that sphere. So the actual takeaway for this point that's going to give us our upper rho bound is that it's on this sphere. And so again, you got to do a little bit of algebra, right? You're going to have to write down the rectangular equation for that sphere of radius A centered at 0, 0, A. Write down the rectangular equation and then go through the chapter 1 process, conversion formulas and all that. And what you will find is that when you convert that to spherical coordinates, you get this right here. So again, make sure you can do that. And that gives you your upper bound right there. Anybody see the process? Don't forget your stretching factor. Again, lots of points, glass half full, etc. Easy to forget, so oh my gosh. So try to make a point of writing down all of this all at once. It will help. Okay, I'm going to take this opportunity to give you my sales pitch that I've made before. You got to take your pictures seriously. Don't make a little postage stamp picture. Not only is that hard for you to work off of, it's hard for your reader, aka your grader, right, the person you're talking to make sense out of what you're trying to communicate. Right? So don't make a teeny tiny picture. Take some care. Try to make it look clear. Don't try to sort of, see the picture in your mind. Let your inner oracle just speak to you and then just draw it. That's not a good process, for most of us. Certainly not for me. Do a revise and redo. Right? Draw a picture. It's going to be bad. Right? Right? Me too. Right? My first picture is very often bad, but I learned something from it and then I redo it and it gets a little bit better. And then I learn a little bit more from that redo, and then my third picture usually good enough, not bad. And remember, this is not just an inborn talent, right? Maybe for some people again, but not for me, right? I have over my life practiced how to draw these kinds of things, and I think it's a useful thing for everybody to do. So I encourage you to, learn that technique. Now, you don't have to use my video on this. I guess I have 2 of them. But everything that I know about mathematical drawing, tailored specifically to Math219 needs is in those 2 videos in my miscellaneous topics playlist. And I encourage you to give a look. Again, if you want to find a different resource, that's all good. The proof is in the pudding. Right? So just make sure that you can draw reasonably well, that you learn the techniques, and don't forget to practice. Again, it's a chops thing. You just gotta spend time actually doing it. Okay, and it looks like we're out of time, so we'll draw the line right there. We've got a couple more spherical examples to do, and we'll keep on plugging away. See y'all later. See you on Friday.